Hey everyone, so we're gonna pick up with logistic regression inference stuff. We've kind of talked about how to do a hypothesis test for an individual coefficient to see if there's an association, as well as a confidence interval for an odds multiplier. And now we're going to move into a couple of types of tests that we can do. We're going to try to draw some parallels between what we're doing now and what we did with multiple regression, because though the details of the test definitely do change, there usually is kind of a similar thing that we've already done, which is pretty nice. So our first test is going to be testing whether or not any of the predictors are useful. And so the test that this is similar to is already given in this text. This is similar to our overall f-test that we had in multiple regression, see if any of the predictors were useful in a model. And so if you remember the null hypothesis, we're kind of sticking with this example for the National Hockey League, where we have distance and then these 7 total levels of shot type, which means 6 indicator variables. And so our null hypothesis then is just that all of those slope coefficients are going to be equal to 0. 1, 2, 3, 4, 5, 6, 7. All right, and so then that would mean our alternative hypothesis, it's not, again, that all of them have to be different from 0, it's just that at least one. So at least one of those beta parameters is different than 0. Okay, so that should be like super similar to the overall f-test null and alternative hypotheses, actually probably identical. But the format of the test changes then. And so what we're going to use as our test statistic is this null deviance minus residual deviance. And so we're not like calculating these specifically really at all, but we could think of the null deviance as just a measure of error when using the model with no predictors. Hence the term like null, because it corresponds to this null hypothesis where all the predictors are, or all the slope coefficients are equal to 0. The residual deviance we could think about as a measure of error when using the model with the predictors. So in this case, with shot type and with distance to the goal. Okay, and so from some like stat theory stuff that again we're not really going to talk about, you kind of just have to take the leap of faith and just assume that this is true. Then this test statistic, which we're calling G, if the null hypothesis is true, follows a chi-square distribution, which you probably remember from stat 113. Even if you don't remember the specifics, at least the term should ring a bell. And so this distribution has k degrees of freedom, where k is just the number of parameters in the null hypothesis. And so let's go ahead and calculate this G. And so our null deviance, I'm going way back to, oh, I guess I'm not going that far back. Going one whole page back to page 4, grabbing this null deviance of 1824. That same table has residual deviance. So R is nice and clear, spells it out, 1756. That would mean G, our test statistic, is 68. And our degrees of freedom we could get from when we wrote out the null hypothesis, that's just going to be 7. And so you could think about this as kind of larger values of G would mean that there's more evidence for the alternative hypothesis. And the reason that would be is that larger values of G would mean that the residual deviance using our predictors is super different than the null deviance that doesn't use our predictors. And we're thinking about deviance as being some measure of error. So that should make at least some intuitive sense, even though we're not really going into this log likelihood of what the deviance actually is. And so you might have also drawn out chi-square distributions in stat 113, which are typically right skewed. And so you would really need some sort of technology to know where G is going to fall on this curve, but I'm just kind of doing a guess. And then our p-value is the area of the right tail, because we agreed that larger G meant more evidence for the alternative hypothesis. Since we're like interested in this right tail area, that means when we use R, remember this P, we've used like PT, and that gave area to the left. So this P chi-square, that also gives area to the left. So that would give this whole area, but that's not what we want, right? We want the area to the right, and so that's why we've got to do this 1 minus to get the p-value. Okay, so once we've got all that, our last step is just to write a conclusion in context of the problem. And so we want to say there is strong evidence, since our p-value for this test was so tiny, that either shot type or distance or both are associated with whether or not a shot goes into the goal. Then I'll give our test statistic, G, and our p-value, which is so tiny, I'm just going to say less than 0.001. Much like the overall f-test in multiple regression, you're probably seeing that this test is like fine if you're looking to just see if any of your predictors are useful. But other than that, it really doesn't tell you that much, because even from our conclusion, we just know that something's important. We don't know whether it's shot type, we don't know whether it's distance, we don't know whether it's both. This is just a test to see if kind of any of the predictors that are candidates might be useful for predicting the probability of a shot going into the goal. Okay, and so next time we'll get into this last test, which we followed the same pattern in multiple regression where we did inference about an individual coefficient, which we did in the last video, seeing if any of the predictors, so testing all of the beta coefficients at the same time, which we did in this video, and then the next video we'll be testing whether just some of the beta parameters are different than 0. And so that kind of corresponds with the nested f-test that we did in multiple regression. All right, as always, let me know if you have any questions.